Calculus is one of the most powerful and beautiful tools in all of mathematics. But for most people, it feels like an impossible subject. Why? Because almost everyone is taught it the wrong way. Teachers throw strange symbols at you, dy over dx power rules, chain rules, integration by parts, and expect you to memorize them. Your brain memorizes these formulas for a test. Then poof, gone. You're left with nothing but confusion and math anxiety. Calculus isn't about formulas. It's not about memorizing rules. It's about one simple, beautiful idea that your brain already understands. So what exactly is calculus? Here's the beautiful truth. Calculus is simply the mathematics of change. Stop and think about this for a moment. Everything in our universe is in constant motion. A rocket accelerating towards space, bacteria multiplying in a petri dish, water cascading down a waterfall. Change is literally everywhere. Calculus provides us with the precise mathematical vocabulary and sophisticated tools to describe and analyze this change with surgical accuracy. It empowers us to answer profound questions. How rapidly is something transforming at this exact moment? What's the total amount of change that is accumulated over any given time period? Calculus stands on two mighty pillars: differentiation and integration. Differentiation is your tool for discovering rates of change. Picture yourself with a super-powered microscope that can zoom into any single point on a curved line and reveal exactly how steep that curve is at that precise location. This steepness measurement is what we call the derivative. Differentiation reveals the slope of any curve at any point you choose. It answers this crucial question: what's the rate of change happening right at this instant? Integration works in the completely opposite direction. It's all about accumulation and gathering. Rather than zooming in with a microscope, imagine pulling back with a wide-angle lens and collecting all the tiny changes across an entire span. This process lets us calculate things like total distance covered, the complete area beneath a curve, or the full volume of a three-dimensional object. Integration reveals total accumulation. It answers this fundamental question: what's the complete amount that has built up over this time period? Here's where it gets absolutely fascinating. These two concepts, differentiation and integration, are intimately linked together. This relationship represents one of the most stunning breakthroughs in all of mathematical history, and we'll dive deep into it shortly. But first, let's quickly review what we need from our mathematical toolkit. Don't worry, we're not going deep into these topics, just making sure we're all on the same page. First, we need to understand functions and their graphs. A function is simply a rule that takes an input and gives us an output. For example, the function f of x equals x squared takes any number, squares it, and gives us the result. When we graph functions, we can visualize how the output changes as we change the input. Next, we need the concept of slope from algebra. Remember that the slope of a line tells us how steep it is, how much y changes for each unit change in x. For a straight line, this slope is constant everywhere. Now, let's master the foundational idea that makes every aspect of calculus work: the limit. What exactly is a limit? A limit describes how a function behaves as its input value creeps closer and closer to some specific target value, without necessarily ever reaching that target. Here's a perfect analogy. Picture yourself walking toward a massive brick wall. With each step forward, the gap between you and that wall shrinks smaller and smaller. The limit represents that distance approaching zero. You might never actually make contact with the wall, but you can get incredibly close to it. Let's examine a concrete example. Consider the function f of x equals x cubed. What happens to f of x as x gets closer and closer to 3? Let's create a data table. When x equals 2.9, f of x equals 24.389. When x equals 2.99, f of x equals 26.73. When x equals 2.999, f of x equals 26.973027. As x approaches 3 from the left side, f of x gets closer to 27. Now let's approach from the right side. When x equals 3.1, f of x equals 29.791. When x equals 3.01, f of x equals 27.270901. When x equals 3.001, f of x equals 27.027027. As x approaches 3 from the right side, f of x also approaches 27. Since the function value approaches 27 from both directions, we declare that the limit of x cubed as x approaches 3 equals 27. Mathematically, we express this as the limit as x approaches 3 of x cubed equals 27. But why is this concept so monumentally important? Because it enables us to handle situations where we simply cannot substitute a value directly. For instance, how do we find the slope of a curve at just one single point? Examine the graph of any curve. When we select two distinct points, we can draw a straight line connecting them. This is called a second line. Calculating this line's slope is straightforward, but what happens when we want the slope at just one point, P? A single point cannot define a line by itself. This is precisely where limits become our savior. We can visualize moving the second point Q closer and closer toward P. As Q approaches P, the second line gradually transforms into what becomes the tangent line, a line that just barely touches the curve at point P. The slope of this tangent line represents the instantaneous rate of change at point P, and it's the limit of all those second line slopes as the distance between our points approaches zero. This revolutionary idea forms the complete foundation of differentiation. To summarize what we've discovered, a limit describes what a function is approaching. It's the master key that transforms average rates of change over intervals into instantaneous rates of change at precise points. This understanding leads us directly to our next major topic, derivatives. The derivative stands as the central pillar of differential calculus. In this section, you'll learn the precise definition of a derivative and master how to calculate it using powerful rules. As we established, the derivative of a function f of x, which we write as f prime of x, represents the slope of the tangent line to the graph of f at any point x. Formally, the derivative is defined as the limit of the difference quotient. This quotient represents the slope of the second line, and we take the limit as h approaches 0. While this definition is absolutely crucial for understanding what a derivative represents, using it to calculate every derivative would be extremely time-consuming. Fortunately, brilliant mathematicians have developed a complete set of rules that make differentiation remarkably efficient. Let's begin with the power rule. This is absolutely fundamental. It states that if you have a function, x raised to any power n, its derivative equals n multiplied by x raised to the power of n minus 1. Let's see this in action. If f of x equals x to the power of 5, the power n equals 5. Therefore, the derivative is 5 multiplied by x to the power of 5 minus 1, which equals 5 times x to the power of 4. So the derivative of x to the power of 5 is 5 times x to the power of 4. What about constants? The derivative of any constant always equals 0. This makes perfect sense because the graph of a constant function creates a horizontal line, and horizontal lines have 0 slope, so the derivative of 12 is 0. We can combine these rules beautifully. The constant multiple rule allows you to factor out any constant from the derivative. The sum and difference rules let you differentiate each term of a polynomial independently. Let's differentiate the polynomial 6x cubed plus 9x minus 7. We apply our rules to each term. The derivative of 6x cubed is 6 times 3x squared, which equals 18x squared. The derivative of 9x is 9. The derivative of the constant negative 7 is 0. Therefore, our final derivative is 18x squared plus 9. Next is the product rule. When we have two functions multiplied together, like f of x equals x squared times sine of x, we can't just take the derivative of each part separately. The product rule says the derivative of f times g equals f prime times g plus f times g prime. It's like the distributive property for derivatives. Finally, we have the chain rule, arguably the most important rule in calculus. When we have a function inside another function, like f of x equals the quantity x squared plus 1 raised to the 5th power, we use the chain rule. We take the derivative of the outside function, keep the inside function unchanged, then multiply by the derivative of the inside function. So here, we'd get calculus also provides rules for differentiating sophisticated functions like trigonometric, exponential, and logarithmic functions. For instance, the derivative of cosine of x is negative sine of x, and the derivative of natural log of x is 1 divided by x. These represent just a sampling of the many differentiation rules available. The secret is learning them thoroughly and practicing their application consistently. We've now defined the derivative as the slope of a tangent line and mastered how to calculate it using rules. But what can we actually accomplish with this knowledge? That's our next exploration. The derivative is an incredibly versatile tool with applications that span across countless fields. Let's examine some of the most crucial applications. In this section, you'll discover how to use derivatives to find tangent lines, solve optimization challenges, and analyze rates of change. First, let's revisit tangent lines. We know the derivative provides us with the slope of the tangent line at any point. When we have a point on the curve, we can use the point-slope form of a line to determine the tangent line's equation. Let's find the equation of the tangent line to the curve y equals x cubed at the point 1, 1. First, we find the derivative. The derivative of x cubed is 3x squared, so y prime equals 3x squared. Next, we determine the slope at our specific point by substituting the x-coordinate, which is 1. The slope m equals 3 times 1 squared, which equals 3. Now we use the point-slope form. Y minus y1 equals m times x minus x1. Substituting our point 1, 1 and our slope 3, we get y minus 1 equals 3 times x minus 1. Expanding and solving for y, we discover the tangent line equation is y equals 3x minus 2. Another incredibly powerful application is optimization. This involves finding the maximum or minimum value of any function. Consider a business attempting to maximize revenue or minimize expenses. How do we locate these maximums and minimums? Observe any graph carefully. At the summit of a peak or the bottom of a valley, the tangent line is perfectly horizontal. What's the slope of any horizontal line? 0. This gives us a foolproof strategy for finding maximums and minimums. Find the derivative, set it equal to 0, and solve for x. These x values are called critical points. Let's find the minimum of the function f of x equals 3x squared minus 12x plus 15. First, find the derivative. F prime of x equals 6x minus 12. Next, set the derivative equal to 0, and solve. 6x minus 12 equals 0. Adding 12 gives us 6x equals 12. Dividing by 6 yields x equals 2. This is our critical point. Finally, substitute this x value back into the original function to find the minimum value. F of 2 equals 3 times 2 squared minus 12 times 2 plus 15, which equals 12 minus 24 plus 15, or 3. So the minimum value is 3, occurring at x equals 2. A final crucial application involves rates of change. When a function describes any quantity, its derivative describes the rate at which that quantity changes. For example, if a function h of t gives an object's height at time t, its derivative h prime of t gives the object's velocity. The derivative of velocity, v prime of t, gives acceleration. This is exactly how calculus models and analyzes motion in physics and engineering. We've now witnessed how derivatives analyze function behavior. Next, we'll explore calculus's other side, integration. We've invested significant time in differentiation, which focuses on finding rates of change. Now let's shift our focus to integration, which centers on accumulation. In this section, you'll learn integration's basic concept, understand antiderivatives, and discover how to find areas under curves. Integration operates as differentiation's inverse operation. Integration takes a rate of change and reconstructs the original function. This means that if the derivative of function f is f, then f is called an antiderivative of f. Let's examine a specific example. We know the derivative of x cubed is 3x squared. Therefore, x cubed is an antiderivative of 3x squared. But is it the only possibility? What about x cubed plus 8? Its derivative is also 3x squared. What about x cubed minus 15? Its derivative is still 3x squared. This demonstrates that any function has infinitely many antiderivatives, all differing by some constant. To account for this reality, we add plus c to our antiderivative, where c represents the constant of integration. So the general antiderivative of 3x squared is x cubed plus c. The integration symbol is an elongated s, which historically stands for sum. This connects us to integration's second major interpretation, finding areas under curves. Imagine we want to calculate the area under the curve of the function f of x from point A to point B. We can't apply simple formulas like those for rectangles or triangles. However, we can approximate it brilliantly. We can divide this area into numerous thin rectangles. Each rectangle's area equals its width multiplied by its height. When we add up all these rectangle areas, we get an approximation of the total area. Here's the key insight. The more rectangles we use, the thinner they become, and the more accurate our approximation becomes. The exact area is the limit of this sum as the number of rectangles approaches infinity. This limit is what we call the definite integral. It's written using the integral symbol with a and b as the limits of integration, f of x as the function, and dx indicating we are integrating with respect to x. So we have two apparently different concepts, antiderivatives and area calculation. The amazing connection between them is the fundamental theorem of calculus, which we'll explore next. We've discovered that differentiation and integration are inverse operations. We've also seen that integration can calculate areas under curves. The fundamental theorem of calculus connects these concepts in an absolutely profound way. In this section, you'll master the fundamental theorem of calculus and learn to use it for evaluating definite integrals. The fundamental theorem of calculus, often called FTC, stands as the most significant theorem in the entire subject. It states that if f is an antiderivative of f, then the definite integral of f from a to b simply equals f of b minus f of a. This is a truly remarkable result. It means we don't need to sum infinitely many tiny rectangles to find areas. We just need to find an antiderivative, substitute the upper and lower limits, and subtract. Let's see this in action with an example. Geometrically, this forms a triangle with base 3 and height 6. Its area is 1/2 times base times height, which is 1/2 times 3 times 6, giving 9. Let's verify this using the Fundamental Theorem of Calculus. First, we need an antiderivative of 2x. Using the reverse power rule, the antiderivative of 2x is x squared, so f of x equals x squared. Next, we apply the theorem. We evaluate f at the upper limit, 3, and subtract its value at the lower limit, 0. F of 3 equals 3 squared, which is 9. F of 0 equals 0 squared, which is 0. So the integral is 9 minus 0, which equals 9. It matches our geometric calculation perfectly. This theorem is extraordinarily powerful because it provides a direct method for calculating areas and accumulations without relying on approximations. It's the bridge connecting calculus's two main branches. Now that we can evaluate integrals, let's examine techniques for finding antiderivatives, which is often the most challenging aspect. Just as we developed rules for differentiation, we need powerful techniques for integration. Finding antiderivatives can be significantly more challenging than finding derivatives. In this section, you'll master two fundamental integration techniques: substitution and integration by parts. Our first technique is called substitution. It's essentially the reverse of the chain rule for differentiation. We use it when we encounter a function nested inside another function. Let's integrate 6x times the quantity x squared plus 3 raised to the 4th power. The key is identifying the inner function. Here, it's x squared plus 3. We'll call this u, so let u equal x squared plus 3. Next, we find u's derivative with respect to x. Du over dx equals 2x. Then we solve for dx. dx equals du divided by 2x. So du equals 2x dx, which means 6x dx equals 3 du. Now we substitute u and dx back into our original integral. This gives us 3 times the integral of u to the 4th power with respect to u. This becomes a simple power rule integral. The antiderivative of u to the 4th power is 1/5 u to the 5th power. Finally, we substitute x squared plus 3 back for u and add our constant of integration c. The final answer is 3/5 times the quantity x squared plus 3 raised to the 5th power plus c. Our second technique is integration by parts. This reverses the product rule for differentiation. We use it when we have a product of two different function types, like a polynomial and an exponential function. The formula is the integral of u dv equals uv minus the integral of v du. The strategy is choosing u and dv so that the new integral of v du becomes simpler than the original. Let's integrate x times e to the power of x. We need to choose u and dv. A reliable guideline is choosing u to be the part that simplifies when differentiated. Here, that's x. So we let u is equal to x, which means du is equal to dx. The remainder is dv is equal to e to the power of x dx. We integrate dv to find v is equal to e to the power of x. Now we substitute into our formula, uv minus the integral of v du. This gives us x multiplied by e to the power of x minus the integral of e to the power of x dx. The integral of e to the power of x is e to the power of x. So our final answer is x multiplied by e to the power of x minus e to the power of x plus c is equal to e to the power of x multiplied by x minus 1 plus c. These two techniques, substitution and integration by parts, are incredibly powerful and will enable you to solve an enormous variety of integration problems. Now let's see how we can apply these integrals to solve real-world challenges. We've learned to calculate integrals. Now let's explore their most important applications. In this section, you'll discover how to use integrals to calculate areas, volumes, and solve problems in physics and probability. We've already seen that definite integrals give us areas under curves. But what about finding the area between two curves? The principle is elegant. The area between two curves equals the integral of the upper function minus the lower function. For example, let's find the area between y equals 2x and y equals x squared. First, we find their intersection points by setting them equal 2x equals x squared, which means x squared minus 2x equals 0, or x times x minus 2 equals 0. They intersect at x equals 0 and x equals 2. Between 0 and 2, the line y equals 2x lies above the parabola y equals x squared. So our upper function is 2x and our lower function is x squared. The area is the integral from 0 to 2 of 2x minus x squared with respect to x. The antiderivative is x squared minus 1/3 x cubed. Evaluating from 0 to 2 gives us 4 minus 8/3 minus 0. which equals 4/3. Integrals also calculate volumes of solids. One standard method is the disk method for solids of revolution. Imagine taking any curve and rotating it around an axis, like the x-axis. This creates a three-dimensional solid. We can find its volume by slicing it into thin disks. Each disk's volume is pi times the radius squared times the thickness. The radius equals the function value f of x, and the thickness is dx. The total volume is the integral of these disk volumes. So the volume is the integral from a to b of pi times the square of f of x with respect to x. In physics, we learned that position's derivative is velocity. The reverse is equally true. Velocity's integral is position. This means if you know an object's speed, you can determine how far it has traveled. The definite integral of velocity from time t1 to t2 gives the total displacement over that time interval. Finally, integrals are fundamental in probability theory. The area under a probability density function over any interval gives the probability that a random variable falls within that interval. This is how we calculate probabilities for continuous distributions like the normal distribution, which models everything from SAT scores to human weights. As you can clearly see, integrals aren't just abstract mathematical concepts. They're essential tools for solving real-world problems in science, engineering, economics, and countless other fields. When we combine derivatives with equations, we get differential equations, equations that involve derivatives of unknown functions. These are among the most important and powerful tools in all of mathematics and science. A differential equation doesn't just tell us the value of a function at specific points. Instead, it tells us how the function changes, and from that information, we can determine the entire function. It's like being given the DNA of a mathematical relationship and using it to predict all future behavior. Let's look at a simple but profound example. Population growth. Suppose a population grows at a rate proportional to its current size. If p of t represents the population at time t, then dp by dt is equal to kp, where k is some positive constant. This says the rate of change of population is equal to some constant times the current population. The solution to this differential equation is p of t is equal to p naught multiplied by e to the power of kt, where p naught is the initial population and e is Euler's number, approximately 2.718. Calculus also deals with infinite series, the idea of adding up infinitely many terms to get a finite result. This might sound impossible, but it's one of the most beautiful and useful concepts in mathematics. Think about it this way: 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. If we keep adding these terms forever, we get exactly 1. Each term gets smaller and smaller, and the infinite sum converges to a specific value. The most powerful application of this idea is the Taylor series, which lets us represent any smooth function as an infinite polynomial. For example, the function e to the power of x can be written as e to the power of x is equal to 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the power of 4 divided by 4 factorial, and so on. This means we can approximate e to the power of x to any degree of accuracy just by adding up enough terms of this polynomial. Similarly, sine of x is equal to x minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial, and so on. And cosine of x is equal to 1 minus x squared divided by 2 factorial plus x to the power of 4 divided by 4 factorial minus x to the power of 6 divided by 6 factorial, and so on. These series reveal deep connections between exponential and trigonometric functions. Calculus extends far beyond single variables. In the real world, most phenomena depend on multiple factors simultaneously, and that's where multivariable calculus becomes essential. Think about temperature in a room. It doesn't just depend on time, it also depends on your location. The temperature is a function of x, y, z coordinates and time t. To understand how temperature changes, we need partial derivatives, derivatives that tell us how the function changes with respect to one variable while holding all others constant. For example, partial derivative of t with respect to x tells us how temperature changes as we move east-west, while partial derivative of t with respect to y tells us how it changes as we move north-south. These partial derivatives help engineers design heating systems and meteorologists predict weather patterns. Let's recap this incredible journey through calculus. We started with the foundational concept of limits, the mathematical tool that lets us work with the infinitely small and approach values we can't quite reach. From limits, we built derivatives, which capture instantaneous rates of change and let us optimize everything from business profits to engineering designs. Then we discovered integrals, which accumulate change over time and space, giving us areas, volumes, and total quantities. The beautiful Fundamental Theorem of Calculus showed us that derivatives and integrals are inverse operations, creating an elegant mathematical symmetry. We saw how differential equations use derivatives to describe how systems evolve over time, from population growth to planetary motion. Series taught us that infinite processes can yield finite, useful results. And multivariable calculus extended these ideas to the multidimensional world we actually live in. I strongly encourage you to practice these concepts we've covered. The most effective way to learn calculus is through active problem solving. Try working through problems independently. Here are several practice problems to get you started. Find the derivative of 4x to the power of 4 minus 8x squared plus 12. Find the equation of the tangent line to y is equal to x squared minus 4x at the point 3, negative 3. Evaluate the integral from 1 to 3, 5x plus 2 dx. Pause here and attempt these problems on your own. I hope this masterclass has completely demystified calculus for you and revealed its incredible power and elegance. Thank you for joining me on this mathematical journey.